Well, okay, so uniform convergence is just like regular convergence in this space. Well, let's see. Suppose I have a bunch of functions. Must they have a sequence? Must the sequence converge? Not necessarily. Well, what would you like to know about this space, for instance, for a sequence to converge? Is it complete? There's a question. And here's a big fact from analysis 2, which you'll prove in analysis 2. This, in particular, this space of functions, CB of E, is complete. Very nice. So, in fact, we have a Cauchy criterion, which will allow us to say, without knowing what the limit is, whether a limit exists. Let's just see if the functions converge, if the functions form a Cauchy sequence. So the Cauchy criterion, here's the theorem. Fn converges uniformly to f on E if and only if, well, okay, just no surprises here. For every epsilon bigger than 0, there exists an n such that for all n and m bigger than big N, and for all x and e, the distance between fn of x minus fm at x is less than epsilon. Notice I've just replaced the double norm signs by saying this is true for all x and e. It's the same thing. This is a Cauchy criterion for uniform convergence. Oh, nice. Very nice. So, so look at what this means. Suppose I look at this sequence of functions. Let's how about the first sequence? First function, this is a function. I'm going to define this function going from 0, 1 into the plane R2. So it's a path, right? Here's one path. Oh, I didn't say actually what the image here of this sequence is, but it's true for even when the image is not the real line, but in Rn. So that's what this example is. Here's the first path, f0. Let's make that f1. Okay. That's one function. Let me define another function. How about this one, f2? Let me define another one. How about this function, f3? Oh, let's define another function. How about f4? Okay, don't make me do all of these. Now, what some of you have seen this construction. This is a construction of, the Koch snowflake. And it's a fractal-like construction, right? But what do people say the snowflake is? Well, it's the one you get by taking the limit of these functions. But wait, how do we know the limit exists? Cauchy? Why is this sequence Cauchy? Successive distances are smaller and smaller. In fact, past some point, for a fixed x, all of these terms are going to be close. And you can define the function carefully so that at a half it's always here. So half it stays put, and at 1/4 it stays put, and at 3/4 it stays put, and then extend linearly, right? So what do you have? Fn here, like so. I'm not going to write out those things, right? You can see by construction it's Cauchy. So it converges. Amazing. I know the limit exists. That fractal limit exists. Okay, now of course the next question is, what is its limit? What is the limit? That's another question. What can I say about the limit? Well, here's another amazing theorem. Oh, this gets so great. This is awesome. Look, turns out that if you have a function that converges, sequence that converges uniformly to a function f, and the fn's are all continuous, guess what? The limiting function is continuous. Is that true in general for pointwise convergence? No, but it is true for uniform convergence. The ribbon convergence helps us, means that the limit is, in fact, continuous. And what does that mean for the snowflake here construction? The limiting function is continuous, right? It's continuous. Right? Because of this theorem. We can actually prove this theorem. So let's do that. Well, let's see. How am I going to argue that the limiting function is continuous? Well, would you agree the idea here is to use the following bound. I want to bound the distance between f of x and f of y, yes? I want this to be small. What do I know is small? For a particular fn, I know fn of x and fn of y is small. And I know the distance from f to fn can be made small. So the bound is going to be, it's a classic epsilon over 3 argument. I'm going to look at the distance from f to some fn, and I have not said which one yet. Compare that to the distance from fn at x to fn at y. And then compare that to, help, fn at y to f of y. So we're going to use this bound, which I'm going to refer to as star. I know you wanted a smiley. But I'm going to refer to each of these pieces as cyclops smiley, double smiley, and triple smiley, because I'm going to refer to them. That's the operative bound. Okay, we can do this. We just got to make our choices carefully. So let's fix x, the one we're talking about. So we'll show continuity at x. Now, so for all epsilon bigger than 0, by 1, we'll choose, what's 1? Oh, this is the steps of the proof. We'll choose f sub k so that what's small? Or f sub n so that what's small? So that f sub n minus f is less than what? Let's make it epsilon over 3. Okay? So what this implies then is that cyclops and triple smiley are both less than epsilon over 3. Right? That's the first choice that needs to be made. Good. What's the second choice? Well, what can I say about fn? It's continuous. So for this epsilon, there exists a delta bigger than 0, and I'll need to say what epsilon because I'm about to refer to it. There's a delta bigger than 0 such that if the distance between x and y is less than delta, then what? Double smiley is small. Less than what? Epsilon over 3, because you could make that anything you wanted, right? Oh, okay. So what am I looking for? For this epsilon, I'm looking for a delta that works for f. What delta will work for f? The same one that worked for fn. So we found a delta bigger than 0 such that f sub x minus f sub y is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is epsilon as desired. Our function, or limit